Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and this episode is about something that sounds fantastical, but is becoming a science reality. Paint that can produce electricity from sunlight. It's called quantum dot solar paint, and in this episode, we're diving deep into how it works, where it's being developed, and what it could mean for the future of renewable energy. Whether you're into nanotechnology, sustainability, or just love the idea of a house that powers itself, this episode is for you. It's no secret that solar power is booming. Over the past decade, solar panels have gone in from futuristic tech on rooftops to a regular sight in homes, schools, even parking garages. We've made huge strides. But here's the thing. Even as solar grows, there are still limitations holding it back. Traditional solar panels are made from crystalline silicon. They're rigid, heavy, and expensive to produce. Manufacturing them involves mining raw silicon, purifying it in energy-intensive furnaces, and then slicing it into plates that are framed, wired, and installed in large flat arrays. For homes and businesses that can afford to do all that, it works. But it's not exactly flexible, literally, economically, or logistically. For example, if you live in an apartment, rent your home, or just don't have a south-facing roof, solar probably isn't the option for you. And even when you do have the space, adding solar panels still requires permits, contractors, and thousands of dollars up front. There's also the question of where solar can physically go. Today, solar mostly lives on rooftops or in large-scale solar farms out in open land. But imagine if solar energy didn't need its real estate. The ideal would be to develop technology that could turn any surface into a solar collector. Not just roofs, but walls, windows, fences, and even vehicles. That's where next-generation materials come in. Engineers and scientists are working on solar technologies that are lighter, cheaper, and more adaptable than anything we've ever had before. One of the most exciting directions in that space is what this episode is about. Quantum dot solar paint. Quantum dot is a nanoscale crystal, usually made from an electrically conductive material like cadmium selenide or lead sulfide. We're talking about particles that are just a few billionths of a meter across. That length can be as small as 9 atoms. But despite their tiny size, they behave in ways that are anything but simple. What makes quantum dots special is a phenomenon called quantum confinement. When you shrink a conductive material that is used in quantum dots down to the nanoscale, the laws of classical physics, like those derived by Newton, stop applying. At this point, the much newer and more confusing rules of quantum mechanics take over. One of these rules is that the color of a light of a quantum dot absorbs or emits depends on its size. Here's a simple way to think about it. If you take a bunch of quantum dots made of the same material but in different sizes, the smaller ones might absorb blue light and the bigger ones might absorb red. That means researchers can tune the dots just by changing their size, customizing them to absorb different parts of the solar spectrum. This is a huge deal in solar technology. Most traditional solar cells, like those made of silicon, only absorb a limited slice of solar efficiency. But by layering or mixing quantum dots of different sizes, you can capture a broad range of sunlight, including infrared and ultraviolet light that regular panels mostly ignore. This is because the spectrum of visible light is just a small snapshot of the full spectrum of all light, at the ends of which are infrared and ultraviolet. Quantum dots were first explored for things like display screens and medical imaging. You might have already seen them on your TV if it's branded as QLED. But their ability to precisely interact with light also makes them ideal for turning photons, the little particles that are the smallest units of light, into electrical energy. And that's where the magic happens. When a quantum dot absorbs a photon, or a little piece of light, it excites an electron by knocking it off its associated atom, just like in a regular solar cell. That excited electron has some energy, and can then be harvested to create a current, provided the dots are arranged in the right structure with the right materials around them. The process is still photovoltaic, turning light into voltage, but done with materials you could suspend in a liquid or apply like a coating. So now that we know what quantum dots are and why they're so good at interacting with light, The next question is, how do we turn them into something usable, like paint? Quantum dots can be suspended in a liquid, creating what's called a colloidal solution. Basically just a liquid with tiny particles evenly spread throughout. This solution can be mixed with binders and other chemicals to form a coating that can be applied like paint or ink. When sunlight hits this painted surface, photons excite electrons inside the quantum dots, and then these electrons move through a network of materials that capture their energy. To make this work, quantum dot solar paint must be built up in multiple layers. From top to bottom, first there is the absorber layer, where the quantum dots capture sunlight and generate electrons. This is the basis of the technology and is the part that actually collects the electricity from the light. Second, the electron and hole transport layers, which help guide those excited electrons toward electrodes, which are the things that allow the electrons to turn the energy they have from their vibration and spin into electrical energy. And finally, the substrate layer, which can be flexible or rigid. This provides the base for the paint and allows it to actually function as paint. Applying the paint is straightforward, just like any paint. It can be sprayed, brushed, or printed over large surfaces, allowing solar cells to be made on walls, windows, or even curved objects. The challenge is balancing efficiency, stability, and safety, while maintaining a low cost and ease of application. Now that we've talked about how quantum dot solar paint works scientifically, let's zoom out and see what researchers and companies around the world are doing to bring this technology to life. One of the most active groups is at the University of Toronto. Their team has been a pioneer in developing colloidal dot solar cells. In their labs, they've achieved efficiencies of around 13 to 15% energy conversion efficiency. This might sound low, but this is comparable to traditional solar cells, a technology that's already revolutionary for sustainable energy. We can also use ourselves as another point of comparison. We are less efficient than these solar cells at turning the chemical energy we eat into kinetic energy through movement, again proving their efficiency. One exciting innovation that the University of Toronto is developing is flexible substrates, meaning the solar paint or coating can be applied to surfaces that bend or curve, opening up applications beyond static surfaces. Eventually, your backpack that regularly bends and warps might have the ability to create electricity on a walk, or even your clothes could have similar applications. At the National Renewable Energy Laboratory, or NREL, researchers are exploring hybrid solar cells that combine solar dots with another emerging group of materials called perovskites. In solar energy, they usually refer to synthetic compounds with a similar crystal structure that are excellent at absorbing sunlight and converting it to electricity. What makes perovskite solar cells stand out is how efficiently and cheaply they can be made compared to traditional silicon panels. Just like quantum dot paints, these perovskite-based electric panels don't require expensive rigid manufacturing. They can be sprayed or printed onto surfaces at room temperature. In just over a decade, perovskite solar cells have jumped from around 3% efficiency in early experiments to over 25% efficiency in labs, rivaling almost all other solar cells. That rapid improvement has made them one of the most exciting developments in renewable energy. This hybrid approach NREL is using combines the best of both worlds: broad spectrum absorption and tunability of quantum dots, and the high efficiency and easy processing of perovskites. In the context of solar paint, incorporating these perovskites with quantum dots could mean coatings that are not only flexible and easy to apply, but also highly efficient and stable, bringing us closer to the day when we can literally paint our way to clean energy. There are also innovations in Saudi Arabia. The King Abdullah University of Science and Technology has been working on printing transparent quantum dot solar films. This could mean windows that harvest sunlight without blocking your view, a game changer for urban buildings and skyscrapers, especially considering that most modern designs are almost entirely made of glass. Now, you might think that this would be problematic because it would be absorbing the lights and turning it into electricity, meaning that there would be less light coming from the window. However, if you remember, quantum dots can be tuned by changing their sizes to absorb only infrared and ultraviolet light and let the middle area of visible light through, meaning that you wouldn't even be able to tell that the solar paint was there. A company that is working on turning this into an actual product is Ubiquitous Energy. They already have a solar window that works. However, like most of these preliminary products, it is far too inefficient to be useful. There are also some early commercial products exploring the idea of solar paint as a real product. The Sun Believable project was one of the first to create a prototype paint that can generate electricity when applied to surfaces. Back in 2011, researchers at the University of Notre Dame set out to create a paint that could generate electricity from sunlight. Their goal wasn't to beat silicon panels at efficiency, not yet. It was to prove that electricity could come from something painted on a wall. Their formula used titanium dioxide nanoparticles, the same white pigment found in many paints, but coated with cadmium sulfide or cadmium selenide, two compounds known for their photovoltaic properties. These weren't true quantum dots in the modern sense, but they behaved similarly and demonstrated the concept. The team mixed the solar particles into a water alcohol base and applied the paint to conductive glass. When exposed to sunlight, the painted surface did generate electricity. Not a lot, but enough to light up some interest. The efficiency was less than 1%, far below what's needed for commercial use, and far below what's being worked on in labs today. But it was the first proof of concept for this technology that could eventually turn out to be revolutionary. Diving back into the physics, one of the most exciting reasons researchers are so hopeful about quantum dot solar paint is a process called multiple exciton generation, or MEG for short. In traditional solar cells, like the silicon panels you see on rooftops, the conversion of sunlight into electricity works pretty simply. One photon of light hits the solar cell, and if it has enough energy, it excites one electron, knocking it loose so it can flow as electricity. But there's a limit to this. Each photon can only free up one electron, no matter how energetic it is. This puts a cap on how efficient traditional solar cells can be, usually around 30% in ideal conditions. Quantum dots, however, have the potential to change that rule. Thanks to their unique properties, when a single high-energy photon hits a quantum dot, it can excite more than one electron, sometimes two or three, depending on how much energy that photon has. That is what we call MEG. If we can get it to happen consistently, we can see 2 to 3 times more current being generated by the sun's light because of multiple exciton generation. Of course, making this work outside of a lab is a challenge. Researchers need to find ways to collect all those extra electrons before they lose energy or rejoin with an atom. But the fact that quantum dots have this potential is a big part of why there's so much excitement around solar paint. Despite all of this, there are still big challenges to solve before it becomes something you can buy at your local hardware store. Let's start with the biggest one, efficiency. As mentioned before, quantum dot solar cells have reached around 13 to 15% efficiency, which is pretty impressive. But when those same materials are made into coatings or paint applied outside of controlled environments, the efficiency tends to drop, sometimes significantly. It's because it's harder to perfectly arrange all the layers, prevent gaps or defects, and maintain electrical contact against a rough or flexible surface than it is in a lab. Researchers are working hard to solve this, but lab performance doesn't always translate over to the real world, especially when you factor in things like dust, weather, or wear and tear over time. That brings us to the second issue, durability. Many quantum dot materials, especially those based on lead or cadmium compounds, are sensitive to moisture, oxygen, and heat. When exposed to sunlight and the elements, which, funnily enough, is kind of the whole point, they can degrade quickly unless they're protected by complex encapsulation layers. This degradation raises another concern, toxicity. Some of the most efficient quantum dots contain lead, cadmium, or other heavy metals. Even in small amounts, these can be harmful if released into the environment through flaking paint, disposal, or accidental damage. This limits their uses in places like schools, homes, or any area with environmental safety regulations. To address this, researchers are exploring non-toxic alternatives like carbon dots, indium phosphide, or perovskite-inspired hybrids that, despite having cadmium and other heavy metals, are not as environmentally harmful. These may not yet match the same efficiency, but they offer a safer path forward. There's also the challenge of integration. Even if the paint works perfectly, it still needs to be connected to an electrical system. That means wiring, inverters, storage, the same infrastructure needed for solar panels today. So making solar paint plug and play is another engineering hurdle. Also, there's cost and scalability. While quantum dot materials can be cheap to make in small batches, producing them at industrial scales with consistent quality is still a work in progress that will probably result in higher prices, lower quality, and a less convenient product. Developing mass manufacturing techniques that are stable, affordable, and fast will be key to making solar point a realistic competitor to conventional panels. In other words, the idea is real, the physics is proven, but the engineering and safety challenges are what stand in the way of putting this tech on buildings, cars, and gadgets. Still, progress is happening fast. Next, we'll look at how this technology might fit into our future, and what the world could look like if quantum dot solar paint becomes a part of everyday life. Can you imagine waking up in a house that powers itself? Not with bulky solar panels stuck to the roof, but with walls that quietly harvest sunlight through a coat of high-tech paint. The color doesn't matter, the shape doesn't matter, it just works. Office buildings could become virtual solar farms, generating energy from their facades instead of just their rooftops. Cities could be transformed, not by tearing things down, but by recoding the infrastructure we already have. Bridges, fences, street signs, noise barriers. Every flat or curved surface could become part of the energy grid. In transportation, cars could be coated in solar paint to extend the range of electric vehicles. Even if they don't run completely on solar, every bit of captured sunlight reduces the load on the grid. Planes, boats, drones, and satellites could benefit too. This might even be the technology that pushes electric planes over the edge to make them more efficient and more widely used than gas planes. And then there's wearable tech. Clothing, backpacks, or tents coated in solar paint could charge phones, sensors, or lights during the day. Perfect for remote work, campers, disaster zones, or military deployments. We could also see quantum dot paint used in emergency shelters, where quick deploy structures could become self-powered just by being unrolled into sunlight. Think disaster relief tents that provide their own lighting and communication tools without external power. The bigger picture here is not just efficiency or convenience, it's access. If quantum dot solar paint becomes affordable, safe, and scalable, it could open up renewable energy to people who can't afford panels, don't have the space for them, or live in places where infrastructure is limited. In a world where climate change demands creative solutions, technologies like this already offer something powerful: the ability to generate energy from surfaces that already exist, without fundamentally changing how we live, just what our surroundings are capable of.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.